Hey, this is Math 8, Unit 7, Lesson 14, Multiplying, Dividing, and Estimating with Scientific Notation. So first thing we want to do is we're going to do a lot of practice today in this lesson. So we're going to be looking at deciding first of all if these are false or true statements. So what I have here is I have a series of things that are multiplied together. Okay, so first thing I can tell is that when you multiply this up together, I should be multiplying a 4 times a 4 to get a 16. I don't see a 16 over there, so that's already telling me I've got something not quite right here. Also, when I multiply base 10s, 10 to the 5th times 10 to the 4th, I add those two things together there, right? And since I add those together, I should end up with 10 to the 5 plus 4 is 9th power. Okay? Over here, what they're doing is they're doing 7 divided by 2, which is true about that part there. And here they're doing 10 to the 6 minus 4, which is true. When I'm dividing, I'm going to divide those things. I'm going to do 6 minus 4, which is accurate. That's an accurate statement. So if I was to work that out, I ended up with 3.5 times 10 to the 2nd when I was all done there. Here, 8.4 times 10 to the 3rd times 2. What they're saying is we're saying, okay, well, let's put the 2, let's multiply that with that number right there. And that's what they're doing there, and that seems to be okay. I don't have a huge problem with that right now. But what I do have a problem with is they went ahead and they tried to combine those together by combining the 3 and the 2. That doesn't work that way. This is a nope, can't do that there. If it had been something to an exponential power, like 10 to the 3rd, the whole thing it was squared, then we would do that. Then that would be okay there. But this is not a square, this is just times 2, so it doesn't work here. So the reality is the only one that actually is true would be this one, and the other ones are both false. Okay, let's take a look at your activity for today, number 2. Activity on biomass. It says use the table to answer the questions about different creatures on the planet. Be prepared to explain your reasoning. Okay, so we're going to use this chart for a whole lot of questions. I'm going to try to go back and forth here. Let's see how I can do this. Which creature is least numerous? Estimate how many times more ants there are. So let's take a look at this. Which one is the least numerous? Now, first of all, it might be a little bit hard to figure that out because they do have different base 10s. This is 10 to the 9th. 9, 9, 10, that's bigger. 16, that's bigger. 3, that's pretty small. 14, bigger. 20, 30, that looks like the biggest, right? So in terms of the least numerous, that's going to be the blue whale. And the reason we can say that is because this has the smallest one, 10 to the 3rd. So you're talking about 1, 2, 3 zeros. And then we have 47. But because 0.47, we're going to go with something along those lines there. And that's all we have. So we're going to have blue whales is the least numerous, not a lot of those guys around. And how many times more ants are there? Okay, so if ants is here at, this is 4.75, so those are pretty close together. The difference between 3, 10 to the 3rd, and 10 to the 16th, you do 16 minus 3, and that gets you 13. So how many more times? 10 to the 13 times more ants, comparatively. What does that mean? Well, that's 1 with 13 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Put some commas in there, and we have a wild, crazy number like that. That's hundreds, thousands, millions, billions, trillions. So you're talking about 10 trillion times more ants than blue whales. Alright, which creature is the least massive? So mass is here, so looking for the smallest mass here. Okay, so we're going to probably investigate the negative numbers, -6, -4, -8, and the -12th power. So our least one here is going to be our bacteria. How many times more massive is a human? So now we're going to compare the human to the bacteria. Alright, so again, the idea is that comparatively, the human is 6.2 times 10 to the first compared to the bacteria, which is 1 times 10 to the negative 12. So in this case, 6.2 is just 6.2. And then this becomes 1 minus a minus 12. Again, think about 1 minus minus 12 is actually going to be 13, so 10 to the 13th power. So in terms of how much larger a human is compared to a bacteria, okay, you're talking about this being, let's say, again, similar idea, this is going to be moving over here to 62, or 62 with 12 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so once again, what are we looking at? We're talking about 62 trillion times more. Well, that's a whole lot more. Which is more massive, the total mass of all the humans or the total mass of all the ants? Okay, so to do that there, what we have to do is do some multiplication between humans and ants to figure out which one has the most. Okay, so humans, and this is the number and the mass there, so we're going to multiply these two things together. So to multiply those things together, what we end up doing is we have 7.5 times 6.2. All right, if we just estimate that there, let's just do it for now, estimate it. Let's say this is about 42. Just for now, let's get rid of the decimals. Okay, let's say it's 42. And this is times 10 to the, we're going to add those up, 10th power. I don't want to leave it as a 42, so I'm going to go ahead and move that over one spot and make it 4.2. And if I'm going to go to the left, this goes up 1 times 10 to the 11th. Now for the ants, we're going to do 5 times 3 is 15 times 10 to the, and again we're going to add this up, 16 plus minus 6 is the 10th power there. I want them to be in a common form, so actually I could probably go back and I can keep this as a 10, and I could say, well, it's 42 times 10 to the 10th. So which one's actually going to be bigger? Well, in this case here, because we're comparing this one with that one, we would say that this one is going to be larger. So the humans have more mass than all the ants. And about how many times? Well, 15 times what gets you to 42? Well, that's about 3 times as much, because 15 times 3 equals 45. And again, we were just estimating. All right, and our last one, which is more massive, the total mass of all the krill or the total mass of all the blue whales? All right, so doing krill versus blue whales. So for our krill, we're talking here about something along the lines of, this is about 8, just estimating, this is about 5. So 8 times 5 is 40, times 10 to the, add this up, 14 plus negative 4 is the 10th power. That's our krill. And for the blue whales, we're going to do something like 5, estimating here 5 and 2, we'll call that a 10, times 10 to the 3 plus 5 is 8th power. So right away I can see that this one is larger because 10 to the 10th power compared to 15 to the 10 to the 10 to the 8th power. Just makes more sense there. Okay, so we're going to go with the krill. Has more mass. And how much more mass is it going to be? Well, to do that here, I'd have to then put this either in terms of the 8th or put that in terms of the other one. So let's say here we're going to go to move this to the left, which is the left one. So I have 1.0 is 9, right? So that's 1. And if I move this one to the right one to make it 400, that becomes a 9. It probably becomes a 9. So how much more is it? It's about 400 times as much. Okay, so lots of work there. Okay, so like I said, it's gonna be a lot of practice today. So 14.3 is a similar idea. And now we're looking at distances and diameters and mass once again. Okay, so let's take a look here at what we have. All right, so here we go. Use the table to answer the question about the sun, the planets, and the solar system. Sorry, Pluto. Okay, so same idea. Estimate how many Earths fit side by side and would have the same width as the sun. So we're now going to be looking at doing some division stuff here a little bit as well. So Earths and sun. So the sun is, in terms of its diameter, is 1.392 times 10 to the 6. And we're going to see how many Earths would fit there. That means we can divide it by how much one Earth is, which is 1.28 times 10 to the 4th power. Alright, so this bit right there, right, is a very similar. This is almost like the same number. So let's estimate that to be 1. That's okay. Times 10 to the 6 minus 4 is 2. Alright, and what is 1 times 10 to the second? That's going to be equal to 100. So about how many Earths would fit inside? We'd say about 100 would fit inside there. Okay, number 2. How many Earths would it take to equal the mass of the sun? Okay, so now we're going to look at the size, the mass of the sun. The sun's mass is right here at 1.989 times 10 to the 30th. And if we divide that by the mass of the Earth, which is 5.98 times 10 to the 24th, and we're going to estimate this. Let's say this is about what? 1.9 is about 2, and 5.98 is about what? 6. So 2 divided by 6, it's going to be what? 1/3 times 10 to the, and 30 minus 24 is the 6th power. So 1/3. Now 1/3 is a decimal, is about 0.3. Okay, so 0.3, and it goes on forever. 0.333, whatever you want to say. All right. So if I write it like that, I have 0.3 times 10 to the 6th power. And so if I want to write that out as a regular number to see how much larger it might be, this becomes 3 and 3, and I move this over 6 spaces. So we go 1, 2, 3, 4, 5, 6, decimal point, and put some spaceholder zeros there. And what do we end up with? We end up with 330,000 times, or 330,000 is how many it would take to make the mass of the sun. Okay, how many times as far away from the Earth the planet Neptune is compared to Venus? Okay, how many times far away from Earth the planet Neptune is compared to Venus? So Earth is, where's Earth at? Okay. Oh, here we go. So for Neptune is here at 4.3 times 10 to the 9th, and Venus is here at 4 times 10 to the 7th. Alright, so about how much farther is that going to be? Well, the difference here is that, well, the 4s are about the same, so I'm really comparing 10 to the 9th to 10 to the 7th. So the difference is about 10 to the 2nd. 9 minus 7 is 2, and 10 to the 2nd is 100 times, it's about 100 times further. And finally, how many Mercuries it would take to equal the mass of Neptune? Neptune is sitting at 4.3 times 10 to the 9th, and Mercury, oops, sorry, that's the distance, sorry about that. So Neptune's mass, I'm sorry, is 1.024 times 10 to the 26, and Mercury's mass is 3.3 times 10 to the 23rd. And so again, what do I have? That it becomes about 1/3, or 0.33 times 10 to the 26 minus 23 is 3. Alright, and so we could put that down as 3, 3, and add one more 0, right? Why that? Because we're going to go over 1, 2, and 3. So it's about 330 Mercuries is what it would take to fit inside there, or 333 if you want to be a little more accurate. Okay, Well, let's do another set of practice ones. Again, today is a lot of practice, and so is tomorrow. Professions in the United States. We have architect, artist, programmer, lots of professions, the number of people in that, and their typical salary. So estimate how many times more nurses are there than doctors. So nurses, we're sitting at, in this case here, 3.45 times 10 to the 6, and we're going to divide that by the number of doctors, which in this case here is 6.9 times 10 to the 5th. Again, doing some estimating, this is about 3.45 and 6.9. That's going to estimate out to about a half, right? Okay, that's about 7. Half of 7 is 3.5, so somewhere about a half. That's about a half. And I could write a half as a decimal as 0.5 times 10 to the 6 times 6 minus 5 is 1. Okay, which means I just move the decimal over one spot to write down a number. And so we would say about 5 times as many. So about 5 times as many nurses as there are doctors. Estimate how much money all doctors make put together. So our doctor was at 6.9 times 10 to the 5th, and the amount of money that they make is going to be times 1.87 times 10 to the 5th. Again, estimating here, this is about 7, that's about 2, so we'd say it's about 14 times 10 to the, what do we do this here? I have to add those up because I'm multiplying 10 to the 10th. So as an estimate, what you might say is you might say this is equal to 14 with 10 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and drop back our one placeholders here, and we're at hundreds, thousands, millions, billions, so about $140 billion is about what doctors are going to make all put together there. That's the idea for that one. The next question asks about how much money do all police officers make. Well, police officers, there are 7.8 times 10 to the 5th. So let's do 7.8 times 10 to the 5th. And we're going to multiply that by the number of police officers. So 5.7 times 10 to the 4th. 5.7 times 10 to the 4th. And again, estimating, this is about 8. That's about 6. 8 times 6 is about 48. And we're going to multiply that by 10. We're going to add those up. 5 plus 4 is 9. So we have 48 with 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. So for our police officers, they're going to be making, this is thousands, millions, and that becomes billions. They're making 48 billion all together, compared to, again, our doctors, who are making 140 billion. Okay? Alrighty, and that's the idea. So who makes more money, all enlisted military put together or all military officers put together? Okay, so our enlisted officers, for our enlisted guys, are enlisted, there are 1.16 times 10 to the 6th of them, right? And they make about 4.38 times 10 to the 4th. Estimating 1 times 4 is about 4. And then we're going to add those up. 6 plus 4 is 10. So 10 to the 10th. Okay. Now for our all officers, so all officers, we would say 2.5 times 10 to the 5th, that's the number there are, times what they make, 1 times 10 to the 5th there. So 2.5 times 1 is equal to about 2.5, and then 5 plus 5 is 10. So in terms of what they're making difference here, it's the difference between this and that, so you'd say it's about 2 times greater is what the enlisted guys are making. Okay, so a lot of practice there, and you can read your summary. It just says, hey, we can multiply and we can divide with scientific notation and make things a lot easier there. Let's take a look then at your homework. So take a pause and let's work on the homework together. We're really on your own. All right, here we go. Let's evaluate expression. Use scientific notation. Sure. So we're going to go with 1.5 times 5. 1.5 times 5 is 7.5. And then we're going to add those up. So 10 plus 2 is going to be 12. Here, we're going to do 4.8 divided by 3 first of all. 4.8 divided by 3 is going to be 1.6. And in this one, we're going to do -8 minus a -3. Those are our exponents we're working with. So that becomes a plus. -8 plus 3 is going to be equal to -5. So this becomes 10 to the -5th. Here, we're going to multiply 5 and 4. It's going to equal 20. And again, here we're going to add the exponents up together. So that becomes 10 to the 11th power when I add those up. Add those, multiply those. Here we're going to do some division. So 7.2 divided by 1.2 is actually equal to 6. And here we're going to subtract 3 minus 5. And so 3 minus 5 equals a -2. So that becomes times 10 to the -2 for D. All right, number 2. How many bucket loads would it take to bucket out the world's oceans? Write your answer in scientific notation. Here's some useful information. The world's oceans hold 1.4 times 10 to the 9th cubic kilometers of water. The typical bucket holds roughly 20,000 cubic centimeters of water. There are 10.15 cubic centimeters in a cubic kilometer. All right, so lots of little notes here. All right, so first of all, we know that with the ocean, we have 1.4 times 10 to the 9th. That's how much ocean water there is, and that's in kilometers, or kilometers. We want to turn that now into cubic centimeters. So to do that, we're going to multiply that by, in our case here, the 1015. 10 to the 15th. So when I multiply that together, I can keep the 1.4 the same, and that's going to be times 10 to the, in this case here, 24th power. All right, so that's about how many cubic centimeters there are in the whole ocean. Now a bucket holds 20,000. Now 20,000 can be written as 2 times 10 to the 4th. That's what the bucket's going to be. So what I have here is the ocean, amount of ocean water, and I convert it into cubic centimeters by multiplying it by that. So I get this number, and I'm going to divide that by a bucket, which is 2 times 10 to the 4th. So 1.4 divided by 2 is 0.7, and then 24 minus 4 is going to be 20. And I want to keep it like that. That's not scientific notation, right? I got to move it to the right. So to move to the right means I need to bring that down by 1, so it becomes 10 to the 19. So that's my solution there. Lots of steps. Number 3, the graph represents the closing price per share of stock for a company each day for 28 days. Let's take a look at that graph on the next page. So what we have here is this is the closing price here, and these are my days for 28 days. What variable is represented on the horizontal axis? That's going to be our days. In the first week, was the stock price generally increasing or decreasing? Well, the first week is right here through there, and we can see that for the most part it seems to be increasing. During which period did the closing price of stock decrease for at least 3 days in a row? So when did it decrease for 3 days in a row? Looking for 3 negative drops. We have 1, 2, 3. That sure does look like a decrease between day 7 and day 10, right? 3 days there. Do I see any other ones? That's a 1 day drop. We have a 1, 2 day drop. Here's a 1 day drop, a 1 day drop, and a 1, 2 day drop. So we're going to go between days 7 and 10. Number 4, write an equation for the line that passes through those 2 points right there. Alright, so first of all, let's get a slope. So our slope is going to be y2 minus y1 over x2 minus x1. So our y2 is going to be negative 2.5 minus our y1, which is 11, over x2 minus x1, negative 8.5. So negative 2.5 minus 11 is going to be negative, in this case here, 13.5. And then this is 5 plus 8.5, which is 13.5. So you end up with simply negative 1. So now we know that we have y equals negative 1 as our slope, x, but we had that y-intercept value right here. It has to go there. So we're going to plug in some values of x and y to solve for what this box value might be. And again, you can pick whichever one you wanted to do. Okay, it wouldn't make a difference. You can pick the 5 and the 2.5. So let's do that. Let's use these points and plug them in to find out what this b value is going to be. So this becomes negative 2.5 equals negative 1 times 5 plus b. So negative 2.5 equals negative 5 plus b. I'm going to add 5 to both sides. So I have 2.5 equals b. So that tells me that my equation will be y equals negative, and I don't have to put a negative 1, I can just write negative x plus 2.5. And there's that one. And number 5, it says explain why triangle ABC is similar to triangle CFE. So why is this triangle here similar to this triangle here? Alright, a couple reasons why. We could say, first of all, that they have the same slope. That might be one thing you could say, right? We're going up 2 over 1, up 2 over 1, up 2 over 1. That's true there. We can also say that I can, yeah. Okay. I can also say that I can dilate with my center being A by a factor of 2, and then translate to C, right? So here I have it's going 1, the distance there is 1, and if I dilate with the center A being this and push it out to 2, I get to there. If I double things up, instead of going 2, it becomes 4. 1, 2, 3, 4 gets there, and that doubles up as well. So what I'm saying is we're going to do a kind of a scale factor of 2 to make things that much, and then we're going to translate this whole thing from A to C to plop it in to this point right there. So that's going to be an increase in the scale. I could also do this. I could also go the other way. I could dilate, or first I could translate first. I can translate C to A, right? Put that to that, and then I can dilate with, in this case here, with a center by a factor of, if that was 2, and it get bigger, go the other way, we go 1/2. So I could do either one of those, and that's going to work just fine. Alright, hope that helps you out with your homework tonight. We'll see you next time.